All right, moments and centers of mass. So suppose we have two different masses. You can think of this like two kids or two people on a seesaw, right? Well, so there has to be a point between the two masses, not necessarily exactly in the middle, in a way that these two masses are in balance, right? Well, so typically the idea is to have the center mass closer, the center of mass closer to the heaviest body to have some balance in this case. All right, so here is a mathematical description of the situation. Well, this is something you've seen in physics. So does that look familiar with that? Well, all right. What was that?
Oh yeah.
Oh yeah. Oh, okay. So, so this means that when we multiply, this is in balance. When the product of mass 1 and distance 1 is equal to the product between the second mass, and the second distance, and the distance 2. So to have more mathematical context of this, so we have this mass 2 and this mass 1, and let's assume that the center of the mass is right here in the middle, for the sake of simplicity. All right. Well, so the thing here is number 1. Mass 2 is what's the distance of mass 2 from the center of the mass? It's actually x bar minus x2. At the same time, so let's call this d2, or yes, d2. Okay, and d1 will be that distance from the center of the mass to where the other mass is located at. Okay, which in this case it's going to be the furthest most, which in this case is x1 minus x bar. So this is what we're going to do. We're going to substitute this d2 over here and this d1 over there. So m1 equals d1, which is times d1, which is x1 minus x bar, and times mass 2 times the distance 2, which is x bar minus x2, which is the position where they are. Well, so in this case, the idea is to solve this equation for x bar, to find the point that is the value of x at which we have to have these two masses so they are in balance. So not in a way that one side is not heavier than the other one. Well, so let's distribute m1 x1 minus m1 x bar equals m2 x bar minus m2 x2. And so let's have all the terms that contain the x bar on one side. So I'm going to have m2, or rather I'm going to have negative m1 x bar minus m2 x bar. That is all terms containing the x bar on the left hand side, and on the right hand side everything else. That is negative m2 x2 minus m1 x1. So we can actually turn all these terms that are with negative numbers into positive. So how about we do that? So m1 x bar plus m2 x bar equals m2 x2 plus m1 x1, or the reverse, m1 x1 m2 x2. Factoring out x bar, the idea of having all these terms containing the x bar is so we can make it a common factor and then divide out everything else to isolate x bar. So that's m1 plus m2 And I'm going to reverse the order here. So that's m1 x1 plus m2 x2, and then divide both sides by the quantity m1 plus m2. X bar will be then m1 x1 plus m2 x2 and divided by m1 plus m2, which is this formula that we have over here, right? Ultimately, it came from the fact that in order to have everything in balance, m1 d1 has to be equal to m2 d2. It's important to highlight the following. So, m1 d1 and m2 d2, these are called the moments, or moments of inertia later in 2D and 3D. And this moment, it's well, actually in physics, I think you call the moment P, if I'm not mistaken. You use the letter P, not the letter M, which is the product of the mass times the distance. And we're going to use this moment thing to determine something more than just the center of mass, actually the moments of inertia. All right. So, well, this means, I mean, of course, are we limited to just have two masses? Well, of course not. I mean, we can have a third mass right here, m3. That would be plus m3 x3 over m3. Maybe one more. m4, just add one more term, m4 x4 plus m4, etc. We can keep adding more masses. I mean, you might remember when you were kids, when you got into the seesaws, well, most likely you have other kids joining on the other sides of the seesaw. I mean, it's not limited to only two bodies, right? So we can have a lot more. I mean, in general, so when we have more points, ultimately, what are we calculating? We're calculating the weighted average. This is something you learn in statistics. X bar equals to the sum of the moments mk xk over the sum of the sum of the masses. I mean, the k represents, the first mass, second mass, third mass, etc., depending on how many we have. Well, what about that weighted average? So that weighted average, when you're calculating your overall grade, for example, you have I don't know, maybe 85% on your exam, which is 55% of your grade, plus an 89 times 0.15, which represents your homework grade, and then the other, okay, that's 55 plus 15, that's 70. The other 30%, whatever that multiply, which is the final exam score, for example, right? And that's how you apply the weighted average. That's what you learn. In case you took a statistics course already, you saw this weighted average already. But well, in this case, we're using this weighted average to find the point where we have to pin this plane right here, or this incline, in a way that it doesn't get inclined at all. All right, so it's in balance. Well, so this is total moment, and this is the total mass. All right. Now, let's move on to the next page. What do we have for the next page? So suppose we have a thin rod or a wire. Again, let's go back to the example of the wire, like we did back in calculus to find its mass. So the density of this rod or this wire, of course, it's going to be variable, because in the manufacturing process, I mean, the material used to come up with this wire, it's not perfectly. It doesn't have an even density, so we can say, well, it has a constant density. So it will always be the case in real world that this density is variable. All right. So this is what we're going to do. So we're going to make our partition, the usual partition that we take to derive an integral, to derive a double integral. So this time we're going to take a partition to get the mass of this wire. And well, so this delta x right here, which is the length of the partition, and this xk right here, that's the distance from, well, from the origin, essentially from the origin of this from x naught, for example, which can be 0. I mean, it's the origin, and well, mass equals density times the length for the linear density. We're not talking about volumetric density, which is the usual density that we're used to, but we will later. All right. So this means, well, coming back from the previous formula, which is the average, the weighted average, sigma m sub k x sub k over sigma mk. Well, this will be approximately sigma m, but what's m? M, it's the moment, or rather m is the mass, I mean, which is rho x sub k delta x times x sub k divided by the total mass, which in this case is sigma rho of x. That's a formula we know from calculus 2, right? So delta x times rho of x. But I mean, in this case, we are finding the weighted average of only this partition. Of course, if delta x is infinitely small, you know, Riemann sum, we're going to add infinitely many of this. This really becomes the integral of x, rho of x dx, divided by the integral rho of x dx, which is the formula that we have over here in the definition box below. So the integral at the top represents the total moment from between a and b, that is x, rho of x dx, and the second integral, the one in the denominator, represents the mass. And this is how we're going to find the center of mass in one dimension is the total moment over the total mass. So, but in this case, we are not going to do it by setting different bodies together and finding the balance point in somewhere in the middle, not exactly in the middle, but somewhere in between. Whatever point that balances the seesaw in this case. In this case, we're going to have well, potentially a solid region for which we will find its center of mass, and that's going to be given by the total moment over its mass. So let's look at one example. So we have a thin 5-meter bar that it's made of an alloy whose density in kilograms per meter is given by this linear equation. Again, I mean, it's an alloy. It's a mixture of different metals, of different materials, and the density it's not going to be exactly the same throughout the entire solid, you know. So that's why we have this function which represents a variable density. Well, so from 0 to 5, well, that's because it's a 5-meter bar, all right? So, and x represents the distance from a particular end on the bar. Find the mass of the bar and the location of its center of the mass. So number one, we have to calculate the mass. M equals the integral from 0 to 5 of rho of x dx. That's the second integral right here. That's the integral from 0 to 5. Well, actually, we do a to b. And that's 1 plus 2x dx. And well, evaluating this integral, so I'm just going to give you the answer to this. This is going to be 30. So the mass of this bar is 30 kilograms, by the way. Let's find the total moment, because in order to find the center of mass, we need to find the total moment, because the center of mass is the total moment divided by its mass. And the total moment, big M, it's given by a very similar integral from a to b, but in this case x, rho of x, dx. That's the integral from 0 to 5 of x times 1 plus 2x dx, which is in this case 575 over 6. That's going to give you the answer, and I'm giving you the answer to this instead of evaluating the calculator, just so you can see the picture of what's next. All right, so the center of mass, x bar, will be the total moment m, big M, over the total mass, little m. That is, in other words, 575 divided by 6 over 30. And this is approximately 3.2. Okay, let's make sense out of this situation. What do we have? Number one. So we have a bar that is, it's 5 meters long, all right? That is, this distance varies between 0 and 5, all right? Well, if the density were constant in this case, that is, we have an alloy for which the combination of the metals is perfect, it's perfectly and evenly distributed, well, then in this case, the center of the mass would be exactly in the middle, right? It would be 2.5. So, did you see? Are you guys with me with this? All right. Well, so it would make sense that we will have a bar with its mass that it's evenly distributed. But in this case, well, they're telling us that the density is variable, and also check what we got. We got the center of the mass, which is 3.2. That is more towards the right. How do we make sense out of it? What is that?
The right side heavier?
Yes, the right side is heavier, but why is this right side heavier? Well, check the function rho of x. It's a linear function with a positive slope. In fact, it's an increasing function. That is that we would get a larger density for larger values of x, which in this case, it should explain why it's heavier on this side than over here, isn't it? All right. So for example, at x equals to 0, the density is 1. At x equals to 1, the density is 3. And then it goes on, gets heavier and heavier, right? What if we had our function rho of x equals 1 minus x squared, for example? Which side would be heavier in this case? The right side would be heavier, right, in this case. So the center of mass most likely would be somewhere here. All right, because I mean, this time it's decreasing, and it's also square, so it should be a lot heavier on the right-hand side than on the other side, right? All right. Did you get to see this in physics? Something similar, maybe without the integrals, or not with the integrals? All right, so now let's extend this idea to 2 dimensions. So centers of mass in 2 dimensions. So of course, the moments of mass for a particular point defined as mass times distance. That's what we defined in the C-cell example in the previous page. So for a planar region, or what we usually call a lamina, again, we're going to have different densities at different points. So for example, see any lamina, whether it's plastic or metallic, again, it's not going to be even in their way. So for sure, maybe one corner for one corner is going to be heavier than somewhere else. And also we have integrals in this case to find the moments of inertia, number one, and the total mass for regions described in this case in 2 dimensions, that is for laminas. All right. Well, so how do we describe this situation right here? So number one, Notice we're going to have an x coordinate and a y coordinate this time. So we're not going to look over a line which is basically, I mean, some value in between the two endpoints. In this case, it's going to be a coordinate right here. For example, if we have a square region, and if in this case we know for sure that the density is constant and it's the same at all points, well, the center of mass will be exactly in the middle, right? In the middle of this square. Come on. Right here, right? But if it's somehow heavier to the left and heavier towards this point, well, the center of mass would be here. And that's where we would have to put a pin, for example, to keep it in balance, right? For this case, let me see if it's evenly distributed. Well, maybe not. I don't think it's sharp enough to go through. Yeah. Anyway. This should be all right. Well, not really, right? It's not in balance, right? So so this paper most likely was not manufactured perfectly well. We also have some air. I'm breathing, and I think it's moving because I'm kind of breathing. Yes, no, it's not perfectly even. So it's heavier here, so most likely I will have to move it towards this point. Oh, come on. Well, it's already bent. It's already bent, so that's not helping. Well, I think I went too far. But do you see, I mean, here is the thing. I would have to guess pretty much every other pair until I find the point of balance, right? We're not going to do that. We have double integrals to get that work done for us, right? So number one, well, to find the moment of inertia in the x direction, check this out, be careful. That moment of inertia with respect x, that means along the x-axis, involves this vertical distance. In a similar way that when we found, solids of revolution, when we have the top function and the lower function, when we rotated about an an x-axis, that involved, a vertical distance between the x-axis or the axis of rotation and any point in the function, right? In the same way, the moment about y that involves a distance involves a horizontal distance. No wonder we have this x multiplying the density function. All right. So just be careful with the variables when setting this up. For example, on the exam, I might ask you to set up an integral for the x-coordinate of the center of mass. So in this case, you will have to choose only one of the integrals, that one that contains a y in this case, not the one that contains the x. Because this y, this x, those represent the distance along about the axis that we are finding the moment for, and the point that will be potentially that center of mass. All right? And well, so really we're finding like the center or centroid. I mean, we call it centroid because, well, again, coming back to the square right here. So this would be the center if it were, evenly distributed about its density. However, if it's heavier on one side, let's say it's heavier here, this is not really the center. We call it a centroid because it's that point not exactly in between, right in the middle on both directions, the x direction and y direction, right? That's actually the point that if we pin like, well, yes, right? Still, has to be somewhere here. Where's my key?
Is the holder making it lighter on one side?
Then now maybe.
You missed the holder.
Oh, it's right here.
So the room.
Let me stab it a little bit. Where's my? Oh, here you are. I know. There's the other. I think there's still the other paper. I think. So maybe here. Hopefully this is the balancing point. All right. No, it's not. Yeah. Demonstration failed here, but I mean, at least you get the point, right? What we're trying to find. Okay, set up the integrals that give the center of mass of the rectangle with vertices 0, 0, 1, 0, 1, 1, and 0, 1. I mean, it's basically the unit square, if we will, right? The square with dimension with a length of side equal to 1. So, let's draw that picture. So 0, 0, 0, 1, 1, 1, and 1, 0. Okay, what about the density function? Be careful, because in this case they're not giving us some row of x equals xy or x squared plus y squared or 3x, you know, any function the usual way we're given. In fact, they're giving us the information in a cryptic way. So, in this case, they're telling us that the density function is proportional to the square of its distance from the origin. They're not giving us an explicit function of x and y. Well, in this case, it's two dimension, it's x and y. So that's going to take us back to like intermediate algebra. Remember those variation problems we solved back in intermediate algebra, like y is directly proportional to the square of x and inversely proportional to the cube of r. I remember those type of problems. And then, well, z varies jointly with the cube of x, the square of y, and inversely with the square root of r, for example. But well, we needed to add this k to make that proportion into an equation. Right? So that's what we're going to do this time. However, in this case, the density function, density which is rho, will be proportional. And by the way, when we read the word just proportional, it should be understood that it is directly proportional. Otherwise, they would say it's inversely proportional or varies jointly with, well, some distance and something else. Okay? So in this case, to the square of the distance. Alright? So that's the statement that we get in algebraic form for what we highlighted in the text of the problem. So number one, well, what is that distance though? I mean, it's that distance from the origin and any point on this square. And that point is x, y. Right? It can be any point, x, y. All right? Well, that's distance squared. So isn't it that distance really like the Pythagorean theorem? I mean, that distance, so that's really rho of x, y equals k times x squared plus y squared. Where did I get this from? Well, this is some x, this is some y. That's what is ordered pair. That ordered pair creates this right triangle, and it's really the Pythagorean theorem, except that we're not using c squared equals a squared plus b squared. We're using the letters d squared for the distance and x squared and y squared for the lengths of the sides of this triangle, right? So, let's see. Number one, let's find the mass. To find the mass, let's write down m equals to the double integral over the region r of the density function, and in this case the density function is k times x squared plus y squared. dA. Well, we're going to turn this dA into dy dx or dx dy based on whether it's easier to go, based on whether it's the region is vertically simple or horizontally simple. In this case, it's either vertically simple or it's actually both, right? So I'm going to go vertically simple because it's easier. It's rather what we're used to. So that's the integral from 0 to 1 and from 0 to 1 of k x squared plus y squared dy dx. And well, this k we can actually take it out of the double integral, that's fine. And we can integrate with respect to y. So k, so that's equal to k times the integral from 0 to 1. And then let's integrate x squared y plus y squared with respect to y. That is x squared y plus y cubed over 3, evaluated from 0 to 1, dx. And again, this upper limit and lower limit will be plugged in our y, because that's the variable we integrated with respect to. So that's equal to k times the integral from 0 to 1. So that's 1 times x squared, that's simply x squared, plus 1 cubed over 3 plus 1/3, minus, well, do we agree that this is going to be a big 0? Because we're going to plug in 0 on both y's right here, and that times dx. So, and well, how do we know we're doing the right work? Well, because this remaining single integral is with respect to one single variable. Okay, that's always a good way to check that we're doing the right work. All right, the integral from 0 to 1. 0 to 1 x squared plus 1/3 dx, and that's going to give us k over k times x cubed over 3 plus 1/3 x, and that evaluated from 0 to 1. That is k times number 1 cubed over 3 plus 1/3 times 1 minus, how about another big 0? Sounds good. And well, so that's 1/3 plus another third, that's k times 2/3, which really reduces to 2/3 k. All right, 2/3 k. So that's only the mass. What do we have for now? Going back to our formulas, let's go back to the previous page very quick. So we got the denominator of the two coordinates. So we need to figure out the numerators, and again, we will have to evaluate two double integrals in this case. So we are evaluating a total of 6 integrals in one single problem, if you think of it. All right? And wait until we get to the three-dimensional ones. We're going to evaluate what is 3 times 3 is 9, so 12 integrals in this case. All right? So that's the mass. Yes, definitely calculator. So number 2, the moment about x. For the moment about x, that's going to be the double integral over the region R of, well, if it's the moment about x, recall that that involves a distance y, isn't it? And that's rho of x, y. And again, we're going to use our same rho of x, y, actually dA. And in this case, well, that's going to be double integral k. What was the function again? So k times x squared plus y squared times y, which is the y that we have from the integral, dy dx. We can go dy dx because we are integrating this over the same region actually. So that's 0 to 1.
So if you were to find the moments in the y, would you have to do dx dy instead?
Doesn't matter because the region is still both vertically simple and horizontally simple. You can do it the other way around. If it should give you the same result. So the only thing we would need to be aware when we have a region that is, for example, vertically simple but not horizontally simple, or the reverse, not vertically simple but horizontally simple. And in that situation, we need to decide with the easiest one so that we don't have to set two double integrals. So, and that'll be overkill. All right, so that's going to be number 1. Okay, let me take the k outside. Double double, 0 to 1, 0 to 1, and that's k times x squared y plus y cubed dy dx, and that's k. We can integrate with respect to y. Oh, I had double k. Never mind. Let me put them together. All right, and that's the integral from 0 to 1 of, okay, with respect to y, that's going to be x squared y squared over 2 plus y to the 4th over 4, and evaluated from 0 to 1 dx. And again, these limits of integration, 0 and 1, should be plugged in into which variable? Y, right? Because we integrated with respect to y. All right. So k integral from 0 to 1. So that's x squared over 2 times 1 squared plus 1 to the 4th over 4. That's the evaluation for the upper limit minus the evaluation at the lower limit, which is 0. But do we agree that if we plug in a 0, or that y squared and y to the 4 is going to give us another big 0? So that's fine. Just abbreviate it with a big 0. No need to plug in all those. All right. dx. And again, how do we know we are in the right track? Because, well, this single integral is with respect one single variable, in particular with respect to x. Okay, so let's do some cleanup here. So that's k times the integral from 0 to 1, and that's x squared over 2 and plus 1/4. Integrating this with respect x, that's k equal to, k times x cubed over 3 times 2 in the denominator makes it a 6 plus 1/4 x, and evaluate it from 0 to 1. All right, let's do upper limit minus lower limit. Well, that's 1 cubed over 6 plus 1/4 times 1 minus, well, evaluating at 0, that's going to be another big 0. And, well, that's 1/6 plus 1/4. That should be, the greatest common factor is 12. And that's going to give us a total of k times 5 over 12. And, well, cleaning up the parentheses, that's 5/12 of k. All right? So that's the integral. That's the integral in this case that gives us the moment about x. The third integral will be to get the moment about y, but that moment about y involves a distance with respect x, rho of x, rho of x y dA over the region R. And, well, we can write this integral again as the double integral k times x squared plus y squared, which is the density function. But in this case, this y that we had over here is going to be replaced with an x, because that's the horizontal distance for the moment about y. And well, so in this case, I'm not going to evaluate this integral. In fact, it's going to give us the same exact value, 5 over 12. Okay. So we got everything we need now. We got the two moments in the x direction and the y direction, and we have the total mass. That's all the information that we need to find the center or the centroid of this this square region with variable density, by the way. So, centroid, that is x, not just x bar, but x bar, y bar. It's a point. That's m sub x over little m, m sub y over little m. Don't get confused with the notation. I know the subscript, when we have a letter as a subscript, that means partial derivative of m with respect to x, but in this case we're not doing that, right? It's just to denote the moment about x and the moment about y. Alright, so the moment about x, which is 5/12 of k over m, which is, what's m? 2/3 k, comma 5/12 k over 2/3 k. Well, simplifying all this, well, the k's go away, so it really doesn't matter what k is. Those are going to get cancelled, and that should give us 5 over 8 comma 5 over 8. So that's the order pair for which we will have the centroid for this square region. That is, okay, let's go back to the picture. So 5 over 8, well, if we divide this into 8 eighths, 5 over 8, well, it's actually, I mean, somehow this point, right? I mean, I just drew that point randomly to denote that distance from the origin. I mean, it's a coincidence that 5 over 8 comma 5 over 8, it's actually somewhere here, isn't it? I mean, it's just a coincidence. Not that I knew that this was going to happen. All right, and well, that's one example of how do we find the centroid on a planar region, on a planar lamina. All right, let's see if we have another example. Well, in some cases, it's a good idea to change coordinates. So no wonder we went over all about what's it called? Polar coordinates, cylindrical coordinates, spherical coordinates, all this, because we are going to apply this to situations about finding the mass, all right? Well, so let's say, suppose the density at any point on a semicircular, well, I think that's going to give us a hint that this is going to be a good candidate to use either, well, in this case we're in two dimensions, so that's polar coordinates. So, the distance from the center of the circle. Find the center of the mass of the lamina here. Alright. So let's go ahead and set up the problem. But number one, let's sketch the region. So, semicircular, well, actually they're not telling us anything about the radius of that circle. Alright? So number one, how about we call this just A? I'm not going to use radius R because that R, I don't want to get confused with the same R that we're going to use when we transform the integral from rectangular to polar. So let's just call it A. We know that the equation of a circle, x squared plus y squared equals, it would be r squared, but in this case our radius r is in terms of a squared, which in this case it's going to be, well, when we solve for y squared equals x squared, a squared. Well, never mind about this. So the thing here is, oh, wait a minute, yes, okay, so again, what's the density function? And again, the density function is given in sort of a cryptic way. So in this case, where is it? So the density at any point on a semicircular lamina is proportional to the distance from the center of the circle. So in this case, it's not proportional to the square of the distance like we got before. In this case, it's proportional to the distance. Okay. So let's start with a mathematical sentence. So that's rho, which is the density, is proportional to the distance. But what's the distance? Isn't it this time? K square root of x squared plus y squared. So that's a distance to any point, right? X, y. And well, when we set up the integral right here, m, to find the mass, that's k square root of x squared plus y squared, which would be, well, either dy dx or dx dy. Let's do dy dx. So we have a problem here. If we use a u substitution to evaluate this integral because of the radical, we would be missing a factor of y outside of the radical that stands the du part of the problem. And again, we cannot use a u substitution. We can use trigonometric substitution if you're treating x squared as a constant, but again, that's going to be overwhelming. So in this case, how about we apply what we know from polar coordinates? Well, so number one, let's rewrite rho of xy as a function of r theta. How about a function of r theta? So rho will be really k times the square root of x squared plus y squared, which is r squared. But what's the square root of r squared? Isn't that rho kr? What is that? Oh yes, a. That's true. We're going to use a in this case. Oh no, a is going to be for the limits. So yeah, we use the r for the transformation for the system. But what's the radius? Well, for our situation, that's going to be denoted with an a.
So r is the variable, a is the constant.
Exactly, whatever radius r is in this case. So m equals r. So that's kr. And well, dy dx in polar coordinates becomes r dr d theta, right? R dr d theta. And in this case, well, let's have a look at the limits of integration. Well, the innermost integral, which is the radius, that's between 0 and a. So we didn't use the same letter r to avoid confusions between the variable that we use to transform system and the actual radius of the circle, or rather semicircle. But what about theta? Well, because in this case they're telling us the upper semicircle is just going to vary between 0 and pi. All right? And well, so that's going to turn this integral into m equals double integrals 0 to pi and 0 to a. So that's, let me take the k outside, that's just a constant. That's r squared dr d theta. And in this case, we can integrate r squared with respect to r. So that's k integral from 0 to pi and r cubed over 3 from 0 to a. Okay, this looks like a 9. Let me make it look like an a. And d theta. All right, so that's k times the integral from 0 to pi of 1/3 a cubed minus 0 cubed d theta, and well, in this case simply a cubed. So that's k times the integral from 0 to pi, that's a cubed over 3 d theta. But you know what? A cubed over 3, it's another constant. How about we multiply it outside with the k? So this will be k a cubed over 3 integral from 0 to pi d theta. And well, let's integrate d theta. That's just theta k a cubed over 3 times theta from 0 to pi. And that's k a cubed over 3 pi minus 0, which is simply k a cubed over 3 pi. So that's the mass of that semicircular lamina. And that is going to devolve. Notice in this case it's in symbolic value, and that k depends on the proportion and all that, but that a is going to depend on the radius of that semicircle. So we got the mass, that is, we got the denominators of the centroid. Let's evaluate the integrals for the moments. And well, for the moments, what are we going to get? So for the moment with respect x, or the moment about x rather, so that's going to be the double integral of rho of x y dA. Oh, actually that's okay, let me leave a space. Rho of x y dA. Well, what am I missing in this blank space? A y, right? Because it's about x. The moment it's about x, that involves distance y. And over the region R, and in this case, well, transforming this directly, well, that's a double integral over R, so that's k y square root of x squared plus y squared dA. Well, of course, we're not going to solve this problem using rectangular coordinates. We're going to go about polar coordinates in like the previous example. And that's double integral. Okay, the factor k times the radical becomes, what was that? I think it was kr times y. But check this out. Times r dr d theta, number 1. Okay, this dA becomes r dr d theta. Alright? And this kr, that's from the density function transformed into polar coordinates. However, this integral in terms of r and theta has a y that shouldn't be there. That y has to be transformed to polar coordinates as well. And you might remember a couple of relations to convert between x, y, and r theta. So x equals something and y equals something. So anybody remember these two? R cosine theta, r sine theta. All right. So I need to make some room for another r. All right. Oh my God, there's going to be a lot of r, but that's fine. It's just going to be general power rule when it comes to integrating it. So r sine theta. R sine theta, and well, so let's simplify this integral. Oh, that's going to go from 0 to a and from 0 to pi. That is the integral from 0 to pi, 0 to a, and that's kr cubed, in fact. Well, let me take the k outside because that's constant. R cubed sine theta dr d theta. All right, let's evaluate this integral. So this will be k times the integral from 0 to pi of r to the 4 over 4 sine theta, and evaluate it from 0 to a d theta. And again, this integral was done with respect r. That means these limits of integration should be plugged in only in r and not in theta. That's for the next part of the integration. All right. So in this case, k integral from 0 to pi, that's 1/4 a to the 4th minus 0 to the 4th times sine theta d theta. Well, simplifying all this, a to the 4 minus 0 to the 4, that's just a to the 4th. A to the 4th times 1/4, that's a to the 4 times 1 or over 4, which is also a constant that I'd rather take outside with the k and multiply together. So that's k a to the 4th over 4, integral from 0 to pi, and that's sine theta d theta. K a to the 4th over 4, the integral of sine, which is actually negative cosine, so that's why I have this negative in front of the k a to the 4th over 4, and that gets evaluated between 0 and pi. Alright, so negative k a to the 4th over 4 times cosine pi minus cosine 0, or yes, so cosine of pi, isn't that negative 1? So negative 1, and what's cosine of 0? 1, so that's going to be negative 1 minus 1, isn't that negative 2? Times, okay, let me write the whole thing. So that's negative k a over 4, oh, the a is to the 4th power, and that's times negative 2, number 1, 2 over 4, that's a 1/2, and negative times a negative becomes positive. So that's the moment about x. Let's find the moment about y. Well, I ran out of space in my screen right here, but you guys can do it on the back side of the page. So in this case, I'm gonna go here and add one more page. So the moment about y will be the double integral, and that's a rho of x y dA, but what am I missing in this space right here? Not k, for now x, all right? Because the moment about y involves a distance x, a horizontal distance x. Now over the region R, double, okay, so that's x times the density function, which is k, square root of x squared plus, oh yes, x squared plus y squared dA, and again that's the double integral of x k. Okay, so k, it's still k, I'm gonna take it outside, and that was what was that? Okay, so in this case I should write the transformation for x, which is r cosine theta, and then times r, and times r dr d theta. The r dr d theta is the transformation dA from rectangular to polar. The other factor of r was the square root of the distance, and this other r right here, it's because of the transformation of the variable x into polar coordinates. Something cool is going to happen here anyway. Double, oh, and in this case from 0 to a, and from 0 to pi, same limits, and 0 to pi, 0 to a, so that's going to be r cubed cosine theta dr d theta, same process, integral from 0 to pi, integrate r cubed, that's r to the 4th, over 4 cosine theta, and evaluate that between 0 and a. So, and again, these limits of integration, a and 0, only go, we only plug it into the variable r. So that's k times the integral from 0 to pi, and that's a to the 4th over 4 minus, how about 0? Well, I think I did the 1/4 outside, minus 0 to the 4th, and oh, I forgot to do theta here, cosine theta d theta, And well, again, that's a to the fourth minus 0 to the fourth. That's just a to the fourth times 1/4. And I'm going to write that outside with the k. So k, a to the fourth over 0, no, not 0 over 4, rather, integral from 0 to pi, and that's cosine theta d theta. Well, the integral of cosine, which is that's sine from 0 to pi, and that's ka to the fourth over 4 sine pi minus sine 0. But what's sine pi? 0. What's sine 0? So this whole madness is 0.
If you see that, like, from the beginning, just noticing that, like, alright, we're gonna evaluate.
Yes, you can see that, or even geometrically, because of the symmetry of the semicircular, shape, you know. So that means the centroid, which is a point x bar, y bar, equals the moment about x, and over the total mass, and the moment about y. And well, what's the moment about x? What did we get? So isn't that a k a to the fourth over 2 over what's that? The total mass, what was the total mass? Ka cubed. I mean ka cubed over 3 and pi, comma. Oh my god. Well, this one is 0. 0 over ka cubed over pi, over 3 pi times pi. Well, that y coordinate is going to be 0. Well, from here we can cancel the k's. We can cancel the k's. We can cancel, okay, a to the fourth over a cubed, that's a to the first power. And this should be all right. So I'm going to have a weird division. So that's a over 2 over pi over 3, comma 0. But dividing by pi over 3, isn't it the same as multiplying by 3 over pi? So this is a, or rather 3a over 2 pi comma 0.